This video is part 3 of the Unit 9 notes. In this video, we will be covering how to complete two-step stoichiometry conversions. Two-step stoichiometry conversions occur when one variable is the moles from one side of the island, and the second variable is mass, volume, or particles from the other side of the island. So if you're looking at the stoichiometry island diagram, maybe I'm starting from one of these ends here, mass, volume, particles, but I'm not stopping at substance A, I'm going all the way across to substance B. Or perhaps I'm starting with the moles of substance A, and then I'm going all the way across to the other side of the island. So that would take 2 steps in order to get there. For our first checkpoint question, we are starting with 58.1 grams of sodium iodide, and we are trying to find moles of iodine. So since I am starting with one substance and going to another, and it's not moles to moles, this is going to be a two-step conversion. I start by writing out the 58.1 grams of sodium iodide, and I know that this is going to be a two-step conversion. Whatever unit I started with has to go down to the bottom, grams of sodium iodide. And if you were looking at stoichiometry island, when you go from grams of sodium iodide, you have to stop at moles of sodium iodide. So that is what directly connects it. 1 mole of sodium iodide is equal to the molar mass found on the periodic table. So we have 2 different elements here. So you'd have to add up the mass of a single sodium and a single iodine. That mass is going to be 149.89. All right, for our next part, we are now at moles of sodium iodide, so that is going to go down to the bottom. And we are on our way to moles of iodine, which is a diatomic element, so it's I2. The mole-to-mole ratio is always from the balanced equation. So for every 1 iodine, I have 2 sodium iodide. So that's a 1 over a 2. From here, I need to multiply and divide across, and then I need to round my final answer based on significant figures. In my original number here, 58.1, I have 3 significant figures. So our answer for this problem is going to be 0.194 moles of iodine. For our next checkpoint question, we are going to start off with 4.0 moles of glucose, which is C6H12O6. So that was our starting component, and we are trying to find the liters of carbon dioxide. So going from moles of one substance to liters of another substance is going to be 2 steps on stoichiometry island. For my first step, I need to cancel out the unit that I started with. So that's going to be moles of C6H12O6 on my way to moles of my new substance, which they're asking about carbon dioxide here, so moles of CO2. Once I've found the moles of CO2, then I can cancel that out onto the unit that I was looking for, which is liters of CO2. All right, now for filling in the numbers. When I'm comparing moles to moles, that is when I'm using the numbers from the balanced equation. So I have 6 moles of CO2 for every 1 mole of the glucose. The next part, 1 mole is equal to the molar volume for carbon dioxide, which is going to be 22.4 liters. So that number is written on stoichiometry island, so you would not have to memorize it. From here, we're going to multiply across. It looks like I have 2 significant figures in my original number here. So I start off with 537.6, but that is going to get rounded to 540 liters of carbon dioxide. The 0 on the end does not count towards significant figures since there is no decimal, so that is just a placeholder. All right, for our next checkpoint question, it looks like we are going from molecules of substance A to moles of substance B. So that's going to be another 2-step conversion. We have 2.5 times 10 to the 24th molecules of magnesium oxide, and we're trying to find moles of oxygen. All right, so for our first step, we need to cancel out those molecules of MgO on my way to moles of MgO. Then I need to cancel out my moles of MgO on my way to moles of oxygen. 1 mole is equal to Avogadro's number when we were talking about either atoms or molecules. And then the mole to mole is from the balanced equation. So for oxygen, that is going to be a 1. For magnesium oxide, that's going to be a 2. So here we are dividing by Avogadro's number, and then we are also dividing by 2. Now, I didn't mention this before, but when we have scientific notation like this, make sure that you're using parentheses within your calculator. Each of these two numbers needs their own set of parentheses, otherwise the order of operations will get mixed up, and you will not get the right answer. All right, when we divide across here, we are going to be rounding for our two significant figures, and we end up with 2.1 moles of O2. That concludes part 3, which was on two-step stoichiometry conversions. In part 4, in our next video, we will cover how to complete 3-step stoichiometry conversions.